Hello, Brian Weigel here, and in this video we'll be discussing Renfro and Bond's Chapter 4 in Archaeology Essentials, When, Dating Methods and Chronology. Before we begin, I'll quickly tell you about a remarkable find made a few years ago. It seems every few years a new Dead Sea Scroll is discovered along the northwest shore of the Dead Sea in Israel. These are rolled parchment paper that were stored over 2,000 years ago in ceramic jugs in very dry cave environments, and they preserve the written texts of some of the oldest religions in the world. And so written on these scripts are the ink that were inscribed 2 millennia ago, and they're really remarkable discoveries that are found every now and then, and they reference key events from the Holy Land from so long ago. So excellent preservation, and also dealing with time. And so time is really what we're going to talk about in this video. And for most of you, your longest reference point of time is on the order of a lifespan, which could be, if you are fortunate, 70 to 80, 90 years. And you may think about your ancestors in terms of grandparents, potentially great-grandparents, if you're fortunate to still have that knowledge in your family, and going back in time. But for most of us, knowing or having that genealogy that stretches back even into the late 1800s is not really possible, and we've sort of forgotten some aspects of those people, and our concept of what their lives were like and how long ago that was maybe somewhat limited. On the other hand, in your daily routine, you may think of time in terms of when you wake up, or what time you eat lunch, or when you get off work, and then you string those together in a sequence to form weeks and months and years. And you may notice that when you're a young child, or if you have a young child in the house, that their concept or perception of time is different than an adult's. So depending on how old you are, your perception of how long a week or 2 weeks takes. So think of a young child counting down the days to, say, their 3rd birthday takes forever. Whereas if you are retired, days and weeks click by so quickly that it's almost incomparable how quickly time moves. And you may have noticed that if you're a junior or senior in college, that your semesters go by much faster than they did when you were a first-year freshman or even maybe a sophomore. So it's not that time is speeding up itself. Time remains constant. It's opposed to absolute dating, which would focus time and dating on a calendar age or how many years ago. Relative dating can only really tell us if something is older or younger than something else. So how old something is relative to something else. So a few methods that we have already talked about in previous videos are stratigraphy. Without an absolute dating method of something to date that strata, William Stratus Smith, when he worked out the stratigraphy of England, was only able to give a relative age. So the fossils at this strata were older than the fossils above in strata above that layer, so a relative sense. We also talked about seriation, or organization of artifacts by their typology. Without knowing how old something is, you can organize them by their style, and we'll talk about that. Environmental sequences sometimes are relative in nature, and you just know that something is older than something else. You don't know by how much. Other methods are more accurate. So calendars are good. They count time in a systematic way, day by day by day. So a calendar gives you a date on a 24-hour cycle organized by weeks and months and years. Historical chronologies or even historical calendars say the Maya had 2 calendars that were highly accurate that told time. Annual cycles in nature, like tree rings, which add a layer to the tree every year, and it can tell you other things like how wet that year was or how dry that year was, but the important thing is it's an annual cycle, so it tells time on a yearly basis. Other methods that have been developed over the last 70 years or more are radioactive clocks or radioactive decay. And we'll talk about various forms of those and how they can give us fairly good estimates on how old something is in terms of number of years. So in measuring time, there are many different ways to tell time. AD, BC, or Anno Domini, which is focused on a fixed point of 81, and BC, which is anything before 81. Also a similar system, CE or Common Era, or BCE, before the Common Era, for those who want to use a more secular approach to the calendar or clock. So you may not be as familiar with BP, which some people think means before present, but it actually means before physics, or before 1950, which was the invention of radiocarbon methodology in 1949. So they set 1950 as their fixed point of reference. And so forever since that time, radiocarbon chronologies are counting back from a fixed point of 1950. So every radiocarbon date that's been run uses that standard. And that illustrates the need for a fixed point so that as we go further ahead in time, we're now at 2020, 70 years after the first radiocarbon dates were run, we don't change those reference points and the dates don't become out of date the next year. So for example, if you get a radiocarbon date of 400 BP, that suggests whatever organism that was died 470 years ago, or about AD 1550. And you can see how complicated time becomes. It becomes more complicated, as we'll explain in this video, in that a radiocarbon date does not line up with a calendar age that we know of. And so you have to calibrate that date to align it to our calendar system. And that gives you a cal BP date, or a calibrated radiocarbon years ago. So it all becomes quite complicated, but we'll sort it out in this video. So first, let's talk a little bit about relative dating. Deals with sequences, stratigraphic layers, climate, seriation, all methods we've discussed so far. So stratigraphy is not always nice and neatly laid out one on top of the other. It's often disturbed, either through people digging holes into the ground or natural events. Here you see a profile of different activities with artifacts, some of which date, one of which in the middle dates to 1910 AD here. At the bottom of the profile, in or next to, in terms of depth below surface, a Harappan seal that dates to 3rd millennium BC. And the way that happens is a modern tree pit disturbed the profile and moved artifacts around, mixing them up. So it's the archaeologist's job to sort those differences out. Typology is an important method in archaeology. Styles of artifacts or material culture change through time gradually. Here you see European axes that have evolved in style from the Stone Age to the Iron Age. And alongside that, you see cars and carriages and how those styles have changed through time. So without placing a date or an age on these, we can see stylistically how things have evolved in terms of material culture. You also see here examples of ceramics, which are excellent for typological or serological dating through time. This example from Hohokam, American Southwest. Stone tool technology is excellent for developing these kinds of cultural historic frameworks or periods, because stone is not organic and does not decay, so we have quite a lot of evidence of people working stones into tools. So the typology of stone technology goes back 2.5 million years ago, and we can arrange all of the stone tools into three major categories or periods: the upper Paleolithic period, the middle Paleolithic period, and the lower Paleolithic period. And there are a series of different projectile point styles and tool styles that evolved through time, in some cases over the course of hundreds of thousands of years, in some cases over hundreds of years instead. So one thing that's constant is the material culture changes, preference and styles change through time. So here's an example from the Upper Paleolithic, the Paleo-Indian tradition of artifacts in North America. The first of which recognizable stone tool technology in the Americas is the Clovis complex, Clovis projectile points used to hunt woolly mammoth. Those were followed by Folsom technology, and the style shifted as people shifted from hunting woolly mammoths. Their preference in making their projectiles shifted as they started to focus on bison instead. Whether that's functional or just stylistic, we still don't know, but we do know they changed. And then there's a whole series of late Paleo-Indian traditions that come along. So this is typological organization of material culture in time. As a famous case study, looks at the styles of tombstones in Connecticut. Early on, the death head design, like you see here, was popular. You can see the date here of 1730 stamped on the tombstone, and it's actually very well preserved. We can look at these styles and how people's preferences for what they wanted on their burial stones changed over time, and create a seriation by that. The nice thing about this is we can check the seriation because stamped on the tombstone is a date. So you have a relative dating method that we can use and compare with a absolute dating method, or the date or age stamped on the stone itself. So we can check our work of seriation. It's very simple. Like styles go with like styles. And the bars you see here on the right indicate the frequency of, so the wider that bar is, the more tombstones were counted in that decade. So assemblages are arranged in order. You see the death head on the left. The styles preference changed gradually between 1750 and 1800 to the cherub, and starting around 1780, a new design of an urn with a willow stuck in it emerged and gradually became popular and replaced death's head and the cherub. And so by 1840, you don't see death's head or cherubs anymore on tombstones. You see mostly or predominantly urns and willows through time. So popularity of tombstone designs and stylistic changes through time represented in that case study from Central Connecticut. Environmental sequences go further back in time. So we can talk about geological epochs. The Pleistocene, or the age of ice, goes from 2.6 million years ago up to 11,700 years ago. And during that period, there are several glacier and interglacial sequences, or periods of glacial ice advance and glacial ice retreat, which happened on a global climatic scale. By using climate proxy records, we can determine if a specific area was in a glacial period or if it was in an interglacial period, a relatively cold period or a relatively warm period. Deep sea cores are useful for this. This helps us work out worldwide chronologies. Ice cores from Greenland help us to do this. And in particular, climate proxy records. It's a key term, proxy records, like foraminifera, which are little critters that live in the ocean and create a shell and become very sensitive to slight changes in their environment, and they preserve proxies of those shifts in their shells. When they die, they settle to the bottom of the sea, and they are preserved in the silts that pile up slowly over time. And here you see deep ocean core sediments that contain these remnants of past life that help preserve what the water temperature was like, what the air temperature was like. So deep sea cores and ice cores are very important for climate proxy records and reconstructing changes in the Earth's climate over time. Shells of microscopic foraminifera are collected and studied. They're stratified in the sedimentation process at the bottom of the oceans. Shells are proxies for ocean water temperature. And they do this by preserving oxygen-16 and oxygen-18 isotopes in their shells. And we know that these isotopes are either cold preferring or warmer preferring. And the ratio between oxygen-16 and oxygen-18 in these shells tells us fairly accurately what the average temperature of the ocean was at that time. So we can determine glacial or interglacial cycles going back for the last 2.5 million years during the Pleistocene. Another relative dating method is paleomagnetism. You may be aware that the Earth is surrounded by a magnetic field. What you may not know is that magnetic field flips from time to time. These are called polar magnetic reversals. The magnetic field alignment is preserved in certain rocks that form. So as a rock solidifies, it freezes in place, the molecules within it pointing in the directions of either magnetic north or south, depending on the magnetic field at the time. So on the right, you see a paleomagnetic sequence here, and the black aligned shadings are the opposite of the white aligned shades here. And so it's either north or south. It's kind of like a plus or a minus indicator. And every now and then they switch for reasons we don't fully understand. But this gives us a relative dating mechanism that can help us correlate specific times. And often you want to try to align these with a more absolute method so that you can better place stratigraphic sequences in time. So a couple of key concepts to review: environmental dating methods that we use, deep sea cores, foraminifera, the stratification of the ocean sediments can be cored and help us develop a relative climate chronology. Ice cores preserve layers of annual ice that build up on our glaciers in Antarctica and Greenland and provide world climate chronologies. Those ice cores preserve in them little air bubbles from the atmosphere at the time that they were deposited, and we can measure isotopic signatures within those bubbles through time. Pollen dating is a similar type of environmental proxy record that we can use. Vegetation shifts through time help us understand what climate was like, the vegetation climate was like, and what species of plants preferred that period over time. So one of the things that comes out of this, obviously, is measurements of carbon dioxide in the atmosphere. And here you can see, going back to 400,000 years ago, the level of carbon dioxide in parts per million over time. So when climate scientists are telling you that we're in really uncharted territories with respect to atmospheric carbon, that's referring to the last 400,000 years. And you see on the right-hand side of this how our levels go up quite rapidly and seem to be an anomaly in the past several 100,000 years of sequences. This is the primary cause for anthropogenic global warming, or climate change by increasing unnaturally the levels of carbon in the atmosphere. It creates this greenhouse gas. And measuring these environmental proxy records is precisely how we know what the levels are now today in comparison to what they were 400,000 years ago. So absolute dating is a little more straightforward. Calendars, obviously, chronologies. If you have found a coin with the date 1913 stamped on it, you know it was created in 1913 AD. You may have writing that tell what year it is within the calendar system of that culture. Here's a cuneiform tablet that often recorded the date, as used by the ancient Sumerians in Mesopotamia. Tree ring dating, or dendrochronology, is a very accurate annual absolute dating technique. And then there's also radiocarbon dating, which is a method we'll talk about in more detail. Obviously, calendars are excellent. Here's a Maya long count calendar from the Ria Azul tomb in Guatemala. Has the date stamped here on it, 27th of September, AD 417, which is obviously translated into our Latin style calendar, which they did not use, but we can correlate the two and we know what their equivalent is to that date. Other ways of doing this are dynasties. Here's a chart of the Chinese dynasties, which have the equivalent years stamped in before the Common Era. There were long lists of kings and families of rulers in ancient Egypt and ancient China, as well as some of the other ancient civilizations of the world. And these serve as excellent markers, especially if they're writing something down or creating a monument and they stamp the name of the king at the time or the emperor at that time, then we have a good idea of when that was commissioned or built. So all of these different methods span different periods of time. And on the left here, you see years ago going back to 5 million years. And there's a lot of different sort of absolute dating techniques that we can use. Calendars really only useful for the last 3,000 to 4,000 years since writing has existed. Tree ring datings only go back in different areas to about 5,000 years ago, but we'll take a closer look at dendrochronology. It's very specific to region. The radiocarbon method is only useful back to 45,000 to perhaps 50,000 years ago because of the amount of radiocarbon decay. Every 5,700 years or so, you halve the amount of carbon, and so at some point it becomes so small you can't measure it anymore. It's difficult to measure. And so it's really only useful from between about 400 years ago to about 48,000 years ago. Potassium argon dating picks up where radiocarbon is inadequate and goes back further in time, up to 5 million years ago. Other types of radiometric decay, we call them rock clocks, uranium series, fission track, all of these electrospin resonance types of dating, thermoluminescence and optical luminescence dating, all cover different periods of times. And so you can see that these overlapping methods allow us to cross-check and make sure that the data we're getting is as accurate as possible. And it's a good idea to use a highly reliable method like radiocarbon or dendrochronology to check some of the more experimental methods of dating like optically stimulated luminescence, which has not been around as long and is not as accurate. So using multiple methods, we get a better sense of time. So here we'll explain a bit dendrochronology or tree ring dating. It is based on the tree rings, and in some places like the American Southwest, where pueblos were built out of trees centuries ago, it's dry environment, and those are very well preserved. So here the idea is you want to line up the rings. They sort of serve as barcodes, and you can match them because of the varying thicknesses of the tree rings. You can kind of match them together and go further and further and further back in time. So it takes a lot of trees of various ages and it's very meticulous to construct a radiocarbon or a tree ring chronology, but it's highly effective once that work has been done. So this key concept here, tree ring dating, is a method based on the annual cycle of ring growth in trees. The time range varies. In Ireland, it goes back to about 5300 BC, so around 7,300 years ago. It's quite far. In Germany, they pushed it back the furthest to about 8,500 BC, or over 10,000 years ago. So has the longest dendrochronological record, because some of those trees preserve very well in the peat bogs of northern Germany. And the American Southwest goes back to about 6,700 BC. The precision of this method is 1 year, which works fairly well for archaeology. The application of it is that you can directly date wood with an accuracy that is really one of the best methods out there. It helped to calibrate the radiocarbon method and helped to refine it so that it was more accurate and linking it more to a calendar year ago. So it made an excellent cross-check. And that then helped us extend our dating methods back tens of thousands of years beyond what dendrochronology was capable of doing. The limitations of dendrochronology is it's restricted by its region and different species of trees. Only certain species are useful for it. Doesn't really work very well in the tropical environments, and it's limited, as I mentioned, to specific kinds of trees. Let's talk about the radioactive clocks, radiocarbon dating, which is the most widely used method by archaeologists. It was invented by Willard Libby in 1949. In our atmosphere, the carbon is mostly carbon-12. That's its preferred state. There's about 1% of carbon-13, and carbon-14 is actually quite rare and a little bit unstable too. It's formed out of nitrogen-14 in the upper levels of the atmosphere, but it gets absorbed by life, trees and cows, organisms on the ground absorb carbon. We're all carbon-based species. When that organism, whatever it is, from a blade of grass, a stick off of a tree, or a side of beef from cattle, or cow bone, or an animal bone, when that animal dies or organism dies, it stops absorbing carbon and it begins the process of decay. So that unstable carbon-14 wants to revert back to its carbon-12 baseline, and it begins to decay radioactively. Counting that decay, we know its half-life, counting that decay is how the radiocarbon method works. So life absorbs carbon, death decays. The half-life of carbon-14 is 5,730 years. So every 5,730 years, there's 50% less of the material. And so counting that enables us to go back in time by counting the percentage of carbon-14. So key concepts of radiocarbon dating: it's a method based on the regular decay of radioactive isotopes in carbon. It ranges from 400 to 50,000 years ago, and its precision is improving as years go by. Typically, its precision is a standard deviation of 50 to 100 years. I've been receiving dates back that have standard deviations of 30, 40 years commonly. So it's getting more and more refined. Applications on any organic matter that contains carbon. Calibration has to be done in order to align it with the calendar year. And the reason calibration is necessary is because the amount of carbon-14 fluctuates over time and has fluctuated over time. Through proxy records, we've figured out what those fluctuations are, but it means it's not a standard clock like the ticking of the seconds on a clock. So the calibration helps us to align that and work out those kinks. So limitations are, the archaeologist has to very carefully select what it is that's being dated to make sure that you're dating a cultural activity associated with the archaeological site that you're interested in, and not a naturally occurring item that had nothing to do with human activity. So we'll talk more here about radiocarbon calibration. As I mentioned, carbon-14 in the atmosphere has not been constant through time. The radiocarbon clock does not correlate with calendar years ago, and so it has to be linked together. So dendrochronology helped us in discovering that error in radiocarbon and helped us fix it as well. So the divergence in age is such that 5000 BC would equal about 7020 years ago, or it would come out to 6050 BP or before physics. So you can see how they don't specifically line up in terms of the radiocarbon measurement itself. It needs to be calibrated. And this is what a radiocarbon calibration curve looks like, or the probability. On the left axis, radiocarbon date BP, in pink, the probability of the age falling within that range. The gray is the calibrated probability on the bottom axis, and you can see here how it serves to line that up. So a date of about 470 BP has a 95.4% probability of being between 546 and 478 calibrated BP, or years before 1950. So a little bit of physics for us today. Stratigraphy then, our relative dating method that is tried and true, works very well with radiocarbon, because now we can find organics in those soils and date them and see how old each layer is. And then presumably all the artifacts found within that layer date to about that age. And so on the right here, you see starting at AD 1300 and going back to BC 3,500. So stratigraphy, superposition, radiocarbon all come together really to form the foundation of modern archaeology. Here on the left, you see the stratigraphic profile from the Holtzman archaeological site, a site I work on in Alaska, deeply stratified in silts. And you see the calibrated years that I've done. So I've radiocarbon dated bone and charcoal from the profile, and you can see how it gets older through time. So I'm dating the lower layers here, and the probability is that they date from 11,500 going back to 14,000 calibrated radiocarbon years ago. So radiocarbon has really changed archaeology. And I want to give you another case study here, the Shroud of Turin, forensic analysis of this really kind of remarkable artifact that was found. It's a linen sheet that appears to have the impression of Jesus of Nazareth imprinted on it. So some of the forensic characteristics of this, let's go through that first. It is the impression of a body that was buried, and the likeness of that individual was stained on the burial shroud, which was wrapped around the body when they were interred. You can see it on the wrist, has a large round wound, apparently from being pierced. There's a blood stain there. Upward gouge in the side penetrating into the thoracic cavity, appears to have been stuck with a spear. Small punctures around the forehead or scalp indicate that maybe a crown of thorns was placed on the individual's head, suggesting this. There seems to be some swelling in the face. There's streams of blood down both arms on the frontal side of this shroud. Here you can see the front and back images of the shroud. So it's like sort of a negative impression of the body on this shroud. It's claimed to be the burial shroud of Jesus of Nazareth, based on these forensic observations that can be made. And it first appeared at an exhibition in France in AD 1357. So we already know it's hundreds of years old. A piece of it was radiocarbon dated to AD 1260 to 1390, which suggests it's not old enough to be the burial shroud for Jesus of Nazareth. It actually suggests that it dates to the period when it first appeared at that exhibition in France in 1357, because the radiocarbon age falls within that period perfectly. So radiocarbon has demonstrated this quite clearly to be a forgery. The cloth that it's imprinted on is not old enough. There's excellent 3-minute YouTube video showing the ways in which this impression could have been artificially created at that era, during that period, with materials and the knowledge that existed in the 1350s. So other forms of radiometric dating methods that we've mentioned: potassium argon, uranium series dating, fission track dating, thermoluminescence, optically stimulated luminescence, electron spin resonance, genetic dating, all forms of molecular decay or mutation that can be calculated and help us to tell time on an absolute scale of varying degrees of accuracy. Quickly, we'll talk about some of these. Potassium argon dating of volcanic rocks ranges from 80,000 to hundreds of millions of years ago. And similar to radiocarbon 14 dating, potassium decays into argon. You can measure those molecules. Because potassium 40 has a half-life of 1.3 billion years, it has a long reach. It's very useful for hominid evolution, dating of Australopithecus fossils found beneath or in volcanic layers. It gives us fairly accurate absolute dating with obviously a broader precision. Other rock clocks, uranium isotope decay ranges from 10,000 to 500,000 years ago, and it dates calcium carbonate seance stuck to teeth of fossil hominids. Very useful for early versions of the Homo species. It's been used at important sites of Kafse in school in Israel, and also on the Atapuerca fossils that you see pictured here, some of the earliest in Europe. The dating method has been very effective. So Sierra de Atapuerca in northern Spain, one of the world's most important archaeological and paleontological sites known, the most early hominid remains in all of Europe, helps us to date and determine when hominids first arrived in Europe. It's a series of infilled caves that are full of these hominid remains. Multiple dating techniques have been used at the site to collaborate each other. Biostratigraphy, radiocarbon's been used, potassium argon, uranium series, electron spin resonance, and paleomagnetism, just to list a few. So it's been extensively dated. 1 million years of occupation have been documented. The Grand Dolina goes back 1 million to 800,000 years ago and contains the remains of Homo ancestor there. Galleria is one of the cave sites that goes back greater than 780,000 years ago to 200,000 years ago. Cima del El Fontaine, the oldest securely dated hominid site in Europe, 1.2 to 1.1 million years old. A jawbone was found in the sediments of that cave along with stone tools. So you can kind of see here a map of these fissures in the ground, and in some cases these hominids were thrown into the pits, maybe probably intentionally, and in other cases animals have fallen into the pits and been buried in there. But it seems as it was that these caverns were a place of the disposal of dead bodies, to dump them basically into these holes after they were deceased, because there's so many of them in that area. Thermoluminescence dating, we've mentioned, its range goes back to about 100,000 years ago, about 10 to 25% accurate. It's not the most accurate method at this time, but they're refining it. It actually, this is really cool, it dates the mineral exposure to the sun. So if you're dealing with silts or sands and they're buried, they obviously haven't seen sunlight for thousands of years. And if you're able to collect them and send them to the lab without exposing them to light, clay, stone, feldspar, quartz, all minerals that are useful in this kind of context, they can actually activate the molecules and excite them and determine about how long ago they were last exposed to sunlight. It's really a remarkable advancement in rock clock types of technology. All of these dating methods help us to formulate the world chronology going back 7 million years, hominid evolution through time, the development of material culture, and our understanding of the human past, the vast majority of which has not been during periods of writing or have occurred during what we would call prehistory. So some major events, just to mention, earliest invention of stone tools, between 2.5 and 3 million years ago, the Aldewan technology came first, followed by the first major, or I should say the second major stone tool innovation, which occurred a million years later, 1.8 to 1.6 million years ago, the invention of the Acheulean hand axe. Homo sapiens, fully modern, behaving culturally and biologically modern, say between 200 and 100,000 years ago, appearing in Africa. The first Australians arrived 50,000 years ago. The first people in the Western Hemisphere, 14, maybe 15,000 years ago. The first farming societies using agriculture in Southwest Asia show up around 10,000 years ago. The process of domestication of those plants and animals beginning 20,000 years ago. The first states in Southwest Asia, 5,500 years ago. So in a broad sense, you see the key events of human hominid evolution, technological innovation through time that these dating methods help us to pin down. And it really helps us to explain the migration of humans throughout the globe, the evolution of us as a species, our major achievements and accomplishments through time, which is important on so many levels for us to understand where we come from and who we are. Thank you for your attention. A quick list of image credits, and I appreciate your time. Take care.